right, well, if you're here, I hope you're here to learn about managing customized FPGA accelerators with SDSoC. I know there's a lot of terminology, there's a lot of language we're going to go over. If you have questions at any time, please stop me. I'd rather you ask the question than I get through all the slides. I've got, I don't know, about 70 or 80 slides. I don't intend to get through all of them. There's a lot of support material to try and help you understand the material, because a lot of this, if you've got a hardware background with like FPGA experience, this kind of stuff is very easy to understand. But someone who's only written software, C code, things like that, some of the concepts and things are not difficult to understand, but they're different, because programming in FPGA is significantly different. So what I'm trying to do with this is really give you a flavor for what's involved in all of this. So what is SDSoC? So we're going to start with some terminology on this stuff. And first thing that I want to talk about is HLS. What is HLS? It's a tool that Xilinx has, and a lot of this is going to be Xilinx specific, because that's kind of been the focus for the tool set. But high-level synthesis essentially can take C code and translate it to FPGA code. So you, as the programmer, can write your C code. You direct the tool to put it into the fabric, and it will create the RTL. Well, what is RTL? RTL is really register transfer level design abstraction. That's the fancy term for writing VHDL or Verilog. Essentially, when you write code for an FPGA, you don't write code for the FPGA. What you do is you request a design, you request a behavior, and the tool interprets that into what it believes you want. So that could be creating, converting, matrices, multipliers, things like that. But you will create your hardware and accelerators as you create your design. More terminology specifically to SDSoC, how I'm going to use the terms. A platform is essentially your sandbox of resources. It's what you're going to give the tool that it can play with, because the hardware that you use depends on the features that you have depends on the chip that you choose. So if you've got a 3C or a 3E or a 7EV, there's different hardware capabilities that each of these chips have, and you will want to dedicate certain resources for certain interfaces, and you will want to restrict the tool from using those resources. That's really what the platform is. It's that definition of what it is allowed to use to try to come up with solutions for you. Yep, and so then you start working in a solution space. Once you create, I've been describing it to guys here. I think what goes over pretty well here has been talking about a donut, right? You've got a circular thing. You define all the outside of this, which is your interface to your cameras, your memory, or whatever hardware and other periphery you need to talk to. And then that centerpiece is what you leave for the solution space, for taking your algorithm or whatever you want to accelerate and actually put into this accelerated space. So that's part of the process of creating all of this. When I talk PS, I'm talking the processing system. So inside of an MPSoC, a Zynq chip, I don't know if have you guys heard those terms at all? Okay. These are the names of the chips that Xilinx uses, but there is processing. So on a Zynq MPSoC, there is a 4-core or 2-core A53 in there, and then you have the programmable fabric. The programmable fabric is typically referred to as programmable logic. A lot of people like me who've been doing FPGA stuff for 12, 15 years, I'll just call it FPGA because that's what I know it, but although the technology is significantly different now than it used to be. FPGA, for people who don't know, field programmable gate array. I'm sure we're somewhat know what FPGA is if you're in this room. What are the tools? So the tools for this, you kind of build up from the bottom and go up. It's kind of like a pyramid. Vivado is the base tool that you start creating all of your hardware, and that's where you define the definition of your processor, what utilities, if you're going to use UARTs, USB, etc., what kind of DDR memory you're going to interface to, all the processor-based stuff that you would normally have to create, for your RAS, your CAS, all the definitions of all that stuff. But it will basically support a bunch of these features that I'm not going to go into detail on because I've got 25 minutes to compress 8 hours of information into. But I've left a link here. You guys can go there and read it on your own. But these are all pretty significant, pretty cool features that the tool supports. SDK is the next level up. That's where all of the software stuff happens. That's where, if you've got a collaboration between hardware and software teams, This is where the software guys would work. It's based on Eclipse, so if you're familiar with that, which I assume a lot of you guys, or at least know what most of that is, but that's where you deal with your kernel, your root file system, U-boot, all the stuff that you would need to create your operating systems or bare metal designs happen at this level here. Well, SDSoC, which is why you're here, or at least what I want to talk about, is part of this family of SDX environments. So you've got SDNet, which is software-defined networks. You've got SDXL, which is more of a FPGA to like computer-based accelerator. But the one that we care about is the software-defined accelerators for system on chip, because that's the one that would run on, say, an Ultra96 or something like that. It delivers a lot of system-level profiling, because one of the things that software guys will want to understand is, well, what is the best stuff to put into the FPGA? If you don't understand how to write parallel code, you don't understand what things the hardware can do for you because you don't have that experience, the tools can help guide you on things that it can suggest to be put into the hardware. So a lot of the time it's things that have a lot of for loops, a lot of multipliers, things that if you think about it, you can take mathematically and roll out into many parallel operations. So that's a lot of your artificial intelligence, matrix multiplies, things like that. But it will handle automated software acceleration, which is you tell it, this is the thing I want to put out there, and it deals with that conversion. And the system connectivity. Now that's the big thing that we actually have a lot of customers that use this tool just to generate the connectivity between the processors and the fabric, because you have to create DMAs, you have to create memory movers, but globally it's just coined data movers, and the tool handles all of that for you based on what you've given it as part of that solution space. So in other words, it's an advanced tool suite. It manages all the resources for you. It manages the interconnect between everything, and really it extracts you away from having to configure and create that and have a dedicated hardware team to create that interface and that blend between the software and the hardware. This slide came from, there was another presentation I gave, but essentially it was trying to talk about the difference between HLS and this, but essentially SDSoC manages HLS. That's really what I want you to understand for the sake of this particular course or this particular discussion. But all in all, the thing that you should really take away with SDSoC is that your job, you create this platform, you create that donut, and then you create your solution of what you want it to accelerate, and it takes care of the rest for you. Of course, there's a lot of little things, programming, setting up the spirit of what your code is and things like that, but generally speaking, it takes care of almost everything for you from the stance of that. And it'll work with C, C++, OpenCL. There are OpenCV libraries. It will also work with System C. Like I had mentioned about the pyramid, if you work at the programmable logic level, that's Vivado, your processor SDK, and then SDSoC kind of sits on the top and manages all of that stuff. So why is that important? I think we can all kind of understand and agree that if you're programming code, programming for a CPU is really super easy, right? You just write the code, it just runs. But there's a lot of things you'd have to do. In fact, I caught the tail end of the previous speaker that there's a lot of things you have to do to optimize. There's a lot of things, assembly code to force the hardware to behave a very specific way for your specific use case. Because a CPU is generic. It can handle a lot of things, but it doesn't really do any one thing specific until you start getting into any built-in accelerators. Well, then you've got GPUs, DSPs, things like that, where they're more clock-driven, they're more specific to a specific task, processing video, processing certain high-end mathematical things. Well, FPGAs and things typically sit down here, but if you notice, we've kind of said, well, the ease of development, yeah, programming these things are generally hard because you have to understand the hardware. You have to understand creating VHDL and Verilog and deal with time of flight, such as physically creating logic at this part of the chip, and you have to get the logic across the chip. You have to deal with that as a designer. But essentially what HLS and then by extension SDSoC does for you is it brings this back up here. It makes it a lot easier because it handles all of those little things for you. So it's something to really kind of think about for that. I'm going to skip this guy. A little flavor for what the tool is. So essentially, when I was designing FPGA work, you'd have an unlimited number of buttons to tweak because you have to describe exactly the time of flight, the characteristics of what you're doing. You had to describe every little aspect in order for the system to generate your images for you, to take that sandbox of gates and logic and kind of mush it into something that can process the data that you want. Well, in this case, you don't really get a lot of buttons because you don't need them. The tool takes care of that for you because you've already defined what it's allowed to play with. So in this case, if you have different platforms, it's as simple as you've got your solution and you just click that button, choose a different platform. Now I've just ported it from one system to another. Because I've already given the tool the spirit of what my solution is, it then just takes that to the next donut, that next space, and can recreate a whole new design around that to port from system to system. So that's kind of a really cool thing there. If you want to accelerate different functions at different clock rates, that's as simple as clicking this guy down here. Here's a data path. Remember, I was talking about taking the data from the processing system to the hardware and then back. Well, there's clocks involved in that too. How fast do you want that data to go? Maybe you don't care that it gets there very slow, as long as it's processed quickly and shoved back out. So that was the quick on what those are. You don't have to be an FPGA expert to deal with this stuff. That's really, I think, the most important. Now, there are things you have to understand, because you have to understand how to leverage that hardware, because you are trying to take something that's, you might be running at 2 gigahertz on a A53 and try and run it at 100 megahertz and somehow run that faster. So you have to understand your algorithm. You have to understand how you can describe to the tool to make that accelerate. But the point to this is that you're really looking at this more as a system solution now. You're not looking at it as, I've got this one ARM, and I've got this one chip, and I've got this one thing, and I need to somehow hit that performance target. Now you're looking at it as a system and saying, well, my entire system needs to have this performance level. I don't care about the algorithm anymore, because the tool will help take care of getting me to that performance point. So I ran a real example with this, and this is actually a built-in example to the tool set, but I ran some neat tweaks and things just to get some different numbers to give you a flavor of what's going on. In the C code itself, essentially we have two functions. This is the start the counter. We count the number of clocks by using this function here. It's inlined, so it should be as efficient as it really can be. The tools, the optimization and all that shouldn't be hurting what we're doing. But essentially, you start the counter, you run this. This will run C code normal just on the A53, stop, and it gives us a value. Well, then we run here, do the same thing. But this mmult accel, that has all the hooks to get the data out of the processing system down into the fabric, into the hardware, accelerate it, and then get a result back. And we actually calculate how many processor clocks. So it's a one-to-one, essentially, of how much processor time we're saving. And that's the actual code for that. This is the code for the SDSoC. It's essentially the exact same thing, but we've added these things called pragmas. And there's a few extra things about pushing data around, and we've had to describe how to do that. So that's just to give you kind of an idea about the difference, where this is just straight C. And essentially, that is your C code with just some extra stuff, because we have to describe the spirit of what we want our algorithm to be. And I put that in there. You guys can look at that later, but just to do the side-by-side on what those are. Also, to think about this a little different as well. In software land, we typically talk about flops for performance. That's one way we can say, well, how many floating point operations per second do we get? That helps, and I do realize it's not always a one-to-one between different chips and different things. There's optimizations, hardware accelerators, all that stuff that's built in. But generally speaking, if something has higher flops, it's a better performing system. Well, in programmable logic, we talk clocks. Everything's based on a clock. If you want something to go fast, you make the clock faster, or you make it more parallel. It's not a matter of flops at this point. But the reason we ran this in this way is we're trying to compare it flops to flops, because we're comparing clock cycles in the processor for how long the accelerator took to run instead. In this case, you can see that I have a choice for the data motion of 100, 300, 375. Those are just clocks I added in there. 375 is pushing this fabric a little bit, but I didn't really change the data motion network. What I'm doing is actually changing the speed at which the processing is happening in the programmable logic. And you can see that actually build times, because that's one of the disadvantages in some cases for programmable logic. It takes a lot longer to build this image. But there's a lot of tips, there's a lot of tricks, there's ways you can snapshot certain builds, you can freeze the logic, so it doesn't have to recreate the entire logical solution every time, because you have to consider, you're not just changing your C code to machine code and running it, you're actually creating an entire solution. You're fabricating an entire chip specific to your solution and what you're trying to solve. And I tried to demonstrate that here. You can see that at 100 megahertz, it took me 35 minutes, 34 seconds to run. I ran it a second time. I just changed a couple of things to force it to recreate the logic, but I didn't recreate the entire platform. So most of the platform stayed static. And the tool optimized on its own and saved me about 11 minutes of time. I mean, it's that easy to get that optimization, but if you really get down to locking logic and things, you can knock this down to significantly less time. Well, here you can see I'm trying to stress the system. I went to 100, I went to 300, 375, and the time keeps creeping up. The reason for that is, again, the tool is trying to meet a timing flow, because you have to think of it that if you've got logic placed up here in this part of the chip, and you need to get that logic down here to this part of the chip to do processing, it takes time to push that across the chip. That you normally don't care about, because in an ARM, it's already there. If you want the data to move from here to here, it's as simple as pointing to memory, and it just moves. You don't have to deal with that. It's built in. Well, in this case, you have to fabricate that, or in this case, SDSoC is doing that for you, and that's why it takes longer and longer for it to do this, because it's trying to move the logic around in order to meet that timing skew. Well, here I ran this. I ran it at 100, I ran it at 300, and you can see that I went from 24 times better to 38.5 times better. And then at 375, it actually failed. That means that in this fabric with no optimizations, it could not actually meet timing to get that data from this part of the chip down to this part of the chip, or wherever it needed to move things around. That's how to interpret that. So it's not that the tool really did bad. It's trying to tell you, with what you've told me I'm allowed to do, I couldn't do that. That's physically impossible. But there's other things you can do to optimize it. Like I said, you can change things around. In fact, with some of the tips and tricks and things I know how to do, at 100 megahertz, I could beat the performance out of 375. It's just because you can do those kinds of things once you know how to move stuff around. But this is really just trying to give you a flavor for how this works. And this is an example you can get if you have some way to run it. This is all built into the tools, by the way. So I tried to put this in a better format to kind of show what's going on. And the real summary is down here, that it's a 32 by 32 multiplier. I ran it 1,024 times. It just looped on itself. Essentially, it created a random set of data, 32 by 32. It ran the calculation, calculated everything out. Then it did it again, and then it did it again. And it would do that for the processor only, and then it would do it for the PL only, and then it would do the comparison between the two. And you can see that here I'm running the PS at 1.2 gigahertz, and it took 1.5 million clocks. Well, then that same thing took 65,000 at 100 megahertz, but then at 300, it only took 40,000. So it's not a direct linear translation in this particular case. But we do see a 39x increase here, and just by going from 100 to 300, so I click one button, I got a 1.6x increase. That's not very linear, because it should have been 3x. We went 3 times the clock speed, and I didn't lie to you earlier when I said everything is based on a clock. If you make the clock faster, everything will be faster. So why is that? Well, in this case, you have to think about it that you've got your processing system, this is all the hardened IP that's just like a normal ARM that you're using. But then you've got this yellow block here, which is all your programmable logic. That's the sandbox of stuff I can play with. Well, it takes time to get that data out of here, down into here to be processed. That's why it's not linear in this particular case, because we had a volume of data that had to move. And remember I said earlier, I pointed out specifically there was that 100 megahertz pull down, and I said I'm not changing that. Had I changed that, that would have increased the value as well, because it would have helped move the data faster. So it's very simple to just tweak and change the performance metrics on the system just by once you have that platform set up. So a little bit more breakdown on this. Like I had mentioned earlier, there's this for loop here, and you can notice that we're calling this underscore A instead of A. It's because we need to tell it that you're actually going to pipeline that HLS pipeline. You have to describe that spirit of how you want the data to go through, because this one solution here that's pipelining is not necessarily going to be the right solution for you. If you're doing video, pipelining is great because you push the data through. But there's better mechanisms inside this chip. There's better mechanisms to move a stream of data, and you would ask for a streaming data. This pipeline is just saying, I'm going to have a chunk of data and I want to move it through. And that's because of how clocking works. It's easier to move certain data at higher clock rates even though you're consuming it at lower clock rates. Just because you can push it around, it has to deal with the physics of actually physically moving the data around the chip. Then you get down here, and again, this you can compare later on your own, but you've got your programmable logic that's going to execute in parallel. So I'm just saying you're going to take this thing here and you're going to multiply it by that thing there. But I've got the underscore A, so I'm saying this is a representation of whatever you're going to end up with. I want you to take those things and multiply them. And because of these particular commands here, it's going to take this for loop, and instead of saying, well, I'm going to take this, and then I'm going to loop on itself, and then I'm going to loop on, nope. What it's actually going to do is take every multiplicative element in a 32 by 32 and create a separate multiplication piece of logic for that. So every multiplier is going to get its own dedicated hardware multiplier in this case, just because of how I'm running it. And that's great because now in one clock cycle, I've got all the data. Everything multiplies in one shot. And I think if you go back to this, this data here, I've got it in here somewhere, I worked out that it's something like 4 clock cycles to actually process this entire array. And those 4 clock cycles are because you have to multiply everything. It has to then choose the appropriate answers and then add them together. And it takes time to actually push that through the accumulators and the various DSP elements that create your solutions. I put this in here because I thought it was really interesting to talk about that. Amdhal kind of came up with this formula that describes the parallelism of things, that there's a reason you don't have 32-core, 64-core, 128-core processors. Not only is it very power dense and problematic, but it's how small can you break your problem up? Well, in the case of an FPGA, you can break it down to the atomic level. Like I said, every single element that's being multiplied is going to get its own dedicated piece of hardware. Versus, say, a dual-core, quad-core system, there's only so much you can break up your algorithm and create different threads of what's going to come up with your solution. So that was good there. Oh, here it is. So the PS takes 1,542 PS clock cycles per multiply, versus the hardware is taking 40 to 64, depending on if you're running at 100 or 300 megahertz for the multiplication. So that's really down at the atomic level of how fast this thing really is running and how much acceleration you're getting. So, but again, you're not getting a 40 to 1542 multiplication of acceleration because you have to take the time to get the data into the hardware to manipulate it to push, and pushing it back out. So starting with SDSoC, they have, Xilinx has got this whole family. It depends on where you want to start. Zynq is relatively low. There's low in cost. There's some mid-range stuff. The Ultra96 kind of fits in this range here. And then you can push this stuff up as high as you want to go. If your pockets are deep, you can get bigger and bigger chips with more and more hardware built into it, more and more acceleration, more and more memory. I'm not going to go through this too much in detail, but just to give you a flavor that it is just a processor, right? You're all familiar with ARM. It's just 4 cores of ARM with neon acceleration. You've got the GPU in there. You've got a video codec that's down in the PL that you can access, and all this hardened IP. So all that's built into these Zynq chips. What's important? Oh, you guys have probably seen this out on our bench out there, running a couple different demos. One was motion detection, and one was a kind of like a sign detection algorithm, kind of like using AI kind of stuff. And you know, they're relatively cheap. We've had a lot of people say, well, how much are they? We tell them how much they really for what you're getting, and yeah, they're really not that expensive, especially because this comes with an SDSoC license. Let's see, I got 20 seconds. Let's see. Real quick, your normal development flow, you have your functions. You have to decide which ones you want to put in hardware, which ones you want to put into software. That's a normal flow. However, in SDSoC, instead of that, where if you look at it linearly, SDSoC essentially removes all of that. You just write your code, you put it in there, and the tool then decides based on performance metrics, based on what you've requested, and based on the spirit of what you've told it and explained about what you're trying to accomplish, can split that data up and put it into the various components within there to get the best possible performance. And that's actually this little tick here. You literally right-click the function, say move to hardware, and you can force things into hardware. It handles all your data flow, and you're basically, what I'm trying to show with this is you're down to creating a system within hours instead of days. You don't have to set up a lot of things. The board definitions that we generate, the configuration matrices, the the platforms that we create, you can just leverage all of that and start building on top of that. So as someone who's a software expert, you don't have to understand all of this to the level of creating those bits and bytes and moving things around. We did talk about the platforms. I tried to give you a flavor on that. Let's see, SDSoC does take those platforms, it extends it. I've got an 8-hour course that you can go through that actually goes into a lot of detail on this and is really from a ground up, how do you work with SDSoC? How do you build your own custom platform? Because that's one of the problems that people come up with. Well, that's great, you're giving me this stuff to work with your hardware. How do I use it with my custom thing? Because maybe you've got something to do with video that I haven't thought of and I don't have a reference design for. Well, that's what those courses do. So we try to enable you guys to be able to do that and be able to create your own hardware and software for this so that you can then leverage the amazing power of an FPGA to be able to create your solutions. Try and think of it hardware, DSA definition, which is your hardware definition, so device support archive. It's kind of think of it like a BSP at the level of what your FPGA solution is. And then the SPFM is your software solution on top of that. And SDSoC bridges all of that with this little black box. And you don't need to care what that is. It just works. This was kind of a cool thing just to show that I've created this. You say, well, here's my solution, and it creates all the logic and the programmable logic. So I'm just kind of hammering on the same ideas here. And this is a real design here. This is actually this design. And you can see it added, this is what I gave it as a platform, and then it added all of this stuff here, which is essentially just, that's your processor representation. And this is the data mover that I was talking about coming through. And this is where it starts breaking up the data into things that it can manage and manipulate, because the AXI bus and things like that, they are a specific width, but if your data is only 12 bits, you need to slice that up and to be able to manipulate it. This piece here is your HLS component. Like I said, SDSoC manages that. It says, hey, I want you to create this for me. Well, that's that component there. And then the data itself, then after it gets processed here, gets shoved back into the processor. So that's that matrix multiply design, broken down pictorially. And yeah, so I've got a lot of other slides and things, but I can answer maybe a couple questions. It looks like I've been out of time for probably 2 or 3 minutes. But like I said, I tried to take this 8-hour course and kind of smush it down to 25 minutes to at least give you some feeling, maybe get your toes a little wet on what this technology is. So maybe you can start asking the questions and understand what you don't know so that you can ask the right questions and start moving into some kind of technology like this. So, yes, sir?
And a small question. How is data transferred from CPU to FPGA? Does FPGA see the same memory, or is there some special memory region where you should delay memory?
So how does the processing system move the data to the FPGA? How does the FPGA see that? Is it shared memory? So yes and no. There's a bunch of controllers in between the two that are memory managers. So in the Zynq system, it's called a Snoop controller, and he manages in a round-robin fashion who can access like the DDR memory, because the DDR memory is only a single access, but yet the fabric and the processors have to talk to it. The direct way to talk between the two, there's a fabric called the AXI bus, and that's an ARM standard, and that is actually used to get the data out of the ARM down into the processor or into the processing system of the fabric. And there's 4 or 5 different standards for that. There's streaming, there's DMA access, through the Snoop controller and other mechanisms, like the Zynq UltraScale has a couple other controllers on top of that. But essentially, SDSoC will manage that for you, and you don't need to care. You just need to say, I want this to be accelerated. But at the low level underneath, it will create these interconnects between the AXI, whether it's DMA, or in the case of this design here, everything just goes into DDR memory. There's no AXI between there because it's just up in memory space. And then the FPGA components gain access directly to that memory.
How is it expensive to transfer memory from CPU to FPGA?
How does it what?
How is it expensive? Is it a big lot?
It depends on what your data is. And yeah, so it depends on what your data is and what you're trying to do and how much there is. Because you can think of it like a pipeline. Once the pipeline's primed for video, it's not expensive because the data is continuously flowing. In the case of my matrix multiply, that was what I had worked out on this slide here. So my expenses, like I said, it takes 4 clocks to actually come up with a solution. So 40 minus 4, that's how expensive it is. So 40 minus 4 divided by 2 is 20 clocks to get in, 20 to get out in this particular case, roughly. So it's, in this instance, it wasn't very expensive, but there are other instances depending on how much volume of data there is. Again, it's all programmable, so it depends on what you're trying to accomplish. And SDSoC is very good if you can describe the spirit of what you want in actually gaining that access. So, but I think I'm over time, but we can talk more if there's more questions afterwards. I appreciate all your time. I know I'm eating into Adam's time, so it's okay. All right. So yeah, so maybe this is even a little primer for what Adam's got going on. But yeah, for sure. Thank you for your time and attention. And you know, I know this is all available for you. So if there's other questions, you can get a hold of me or talk to you know, anyone else that's got you know, an Avnet shirt. So okay, thank you.